engineered wood absorbs carbon dioxide and gets stronger. Removing lignin renders wood colorless. Researchers have created a process that can be scaled up, saves energy, and fortifies wood for use in construction so that it can trap carbon dioxide. Since 40% of carbon dioxide emissions are attributed to the production and usage of buildings, structural materials like steel or cement are costly both economically and environmentally. The development of environmentally acceptable alternatives for present materials could aid in reducing carbon dioxide emissions and slowing global warming. Materials scientists and colleagues developed a technique to concurrently address both issues by introducing molecules of a carbon dioxide-trapping crystalline porous material into wood. We already use a lot of wood, a structurally sound and renewable resource. Our engineered wood did demonstrate increased strength when compared to normal, untreated wood. To complete the operation, delignification, a technique, is employed to first remove the network of cellulose fibers that provides wood its strength. Wood is made up of three primary substances: cellulose, hemicellulose, and lignin. Wood turns colorless when the lignin that gives it its color is removed. The lignin may be eliminated with a simple two-step chemical process that uses components that are safe for the environment. After removing the lignin, they use bleach or hydrogen peroxide to remove the hemicellulose. Afterwards, a solution containing minute bits of Calgary Framework 20, MOF, a metal organic framework, is poured over the delignified wood, CAF20. Because of their ability to absorb carbon dioxide molecules into their pores, MOFs are sorbent materials with a vast surface area. The MOF particles fit easily into the cellulose tubes and adhere to them as a result of good surface interactions. One of the numerous cutting-edge carbon capture technologies created to combat climate change caused by humans is MOFs. There is currently no sustainable, biodegradable substrate for using carbon dioxide sorbent compounds. Our wood with MOF enhancements offers a flexible support structure that enables the installation of sorbent in a range of carbon dioxide applications. Many MOFs currently in use exhibit poor environmental stability. A structural material shouldn't have a high susceptibility to moisture, which is a trait of some materials. Yet in terms of performance level and flexibility under varied climatic situations, the CAF20, created by a university professor and colleagues, stands out. An important source of industrial carbon emissions is the production of structural materials like metals and cement. Regarding the materials utilized and the byproducts of processing, our approach is more straightforward and environmentally benign. The following steps would be to set up sequestration procedures and conduct a thorough economic study to ascertain the material's scalability and commercial feasibility.